Hello everybody, I'm Matheus Garcia and I'm the leader of the Inline Fluid Separation Group of TOMOCON. Behind me, you can see the Inline SWIRL separator facility that was built in the Delft University of Technology in the Netherlands for this project and demonstration. The Inline Fluid Separation team of TOMOCON counts with me and 3 other PhD candidates around Europe. Mohamed Sattar in the Delft University of Technology in Poland, Benjamin Sahovic in the Helmholtz Zentrum Dresden-Rossendorf in Germany, and Anand Atman in the Institut National Polytechnique de Toulouse in France. Together, we share the objective of introducing tomography to the control of multiphase flows, and in particular, to the context of inline fluid separation. The TOMOCON project studies 4 potential applications of tomography in the real-time control of industrial processes, namely microwave drawing of porous media, batch crystallization, continuous casting, and, of course, inline fluid separation. The inline fluid separator explores centrifugal forces to separate a mixture of 2 fluids, in this particular study, air and water. The separator works by imposing a rotation to the mixture in the SWIRL element. After the device, the rotating fluids are separated into a core of air and an annulus of water. Air is captured by the pickup tube and water is captured by the water outlet. The separation can be controlled by valves that can be adjusted targeting the capture of the majority of air in the pickup tube with the minimum possible amount of water. Tomography is a natural choice to monitor the inline fluid separator. The technique can measure the distribution of air and water in the flow, which allows us to say if they are being properly captured by the outlets or not. Electrical resistance tomography is used in this project to measure the gas core near the pickup tube, and the core size is controlled in real time via the pickup tube valve. This presentation is divided into 6 sections. First, the experimental facility is introduced. Then, the connection between the flow upstream and inside the separator is explored. The wire mesh sensor and CFD simulations are the next topics, followed by the valve effects in the flow and the description of the electrical resistance tomography sensor. Finally, some controller results are presented. The flow loop used in our experiments runs with a mixture of air and water. The water is stored in the tank right there, and it's pumped up to our separator via one of these 2 blue pumps here installed in parallel. The combination allows us to explore a wide range of water flow rates. Air is injected in the loop in these blue tubes right here through a separator to make sure that the distribution of air is more or less uniform in the cross-section. The system can operate in bubbly, slug, and churn flows. The remaining of the loop and its most important part, the SWIRL separator, is located on the 2nd floor of the facility. Okay, so welcome to our 2nd floor. Here's where the magic happens. Here's our SWIRL separator, and it starts in this yellow element right here that we call a SWIRL element. I'm going to pick an old one for you so you can see the details of its internals. Here we have an old SWIRL element, and this is the first thing that the flow faces. You see that the veins that are inside this element starts parallel to the original flow direction. If you look at the top of the SWIRL element, we see that the veins are now very angled. So what is happening here is that the flow that was first coming parallel to the SWIRL element, after crossing such veins, it has to rotate. So it gets this helical type of motion. The SWIRL element is followed by the SWIRL tube, this region right here, that is just a vertical pipeline. In this pipeline, the separation takes place, because now, as the fluids are rotating, centrifugal forces take place, pushing the water towards the wall of the pipeline and the air to the center of the domain. This air coalesces into a continuous core that's captured by the pickup tube that's placed up here. The pickup tube, if our separation is perfect, should capture all the air, and all the water should go to the outlet around it, the water outlet. These 2 outlets of our domain present 1 valve each, and you can see one of the valves here in orange. By changing these valves, we can make sure that the flow bends to one direction or the other. So you can imagine a condition where the core size is too thin. If the core size is too thin, a lot of water is going to the pickup tube, and this is undesired for us. What we can do then is close the pickup tube valve a little bit more to introduce an extra resistance to the flow to go to that direction. The water, now instead of going to the pickup tube, it faces this extra resistance and it goes towards the outer tube. As a consequence, the core gets a little bit bigger in size and we achieve a better separation. The same thing is valid the other way around. If we have a core that's much bigger than the pickup tube size, then we can open the pickup tube valve a little bit more and reduce the resistance there. This will cause the flow to bend towards that location and the core will shrink in size. The main goal with this setup is to try to adjust the valves in real time to make sure that we're always capturing the best amount of air possible in the pickup tube with the minimum possible amount of water. Our separator ends at the valves, but in this setup we still have these tanks right here. These tanks have flow meters of air and water individually that allows us to compute the efficiency of separation. We do this by comparing the values in each of the tanks with the values that are being injected in the loop. So for instance, if the water flow rate in this tank right here, this is the water tank, is the same as the flow rate of water that's being injected in our domain, then we are capturing all the water in the right outlet. And the efficiency is 100% in terms of water. At the same time, if we are capturing all the air in this tank right here, this is our pickup tube tank, then the flow rate measured there should be the same flow rate of air that's being injected in our domain. As you're going to see later on, it's impossible to have simultaneously all the water going to the water outlet and all the air going to the pickup tube. So we have to find a certain compromise between the two quantities. Now I will turn the facility on so you can see what happens when we have air and water running there. Let's start by looking at the flow taking place at the entrance of our separator in this section right here. Upstream the SWIRL element, the classical vertical gas-liquid flow patterns take place. To illustrate each one of these flow patterns, I will show you some experiments I did keeping a fixed flow rate of water and varying the flow rate of air. When the airflow rate is low, air is distributed into several bubbles, relatively small in comparison to the pipe diameter. With the increase in the airflow rate, some coalescence takes place and there is no longer an uniform bubbly flow in the region. If the airflow rate is further increased, the bubbles can no longer be kept separated and the flow transitions to a slug, where a piston of water alternates with a large bubble that occupies the majority of the pipe cross-section. Each flow pattern upstream the separator has a different impact in the core created inside the equipment, as you're going to see in the next videos. A stable core is formed for upstream bubbly flows. In the pattern, the oscillations in the core interface are small, and the pickup tube valve can be adjusted relatively slow for an optimal separation. When the airflow rate is increased, the upstream flow is no longer an uniform bubbly flow, and the core starts to pulsate. The pulsations happen when the large bubbles cross the SWIRL element. A fast response of the pickup tube valve would be required to capture the pulses that propagate in the core. When the upstream flow transitions to slug, the core oscillations get stronger and the core often shatters into multiple bubbles that are quickly pushed back to the center of the separator. In this case, an even faster response of the pickup tube valve is required to capture all the air in the flow. In our application, the upstream flow is measured by this double-layer wire mesh sensor with an online processing software developed by Benjamin Sahovic at HCDR. The wire mesh sensor consists of two sets of parallel wires, installed perpendicular to each other forming a virtual grid. With voltage applied in the transmitter wire and current measured in the receiver wires, the sensor can measure the electrical conductivity of the intersections in the grid, that is converted to the air-water distribution based on the electrical properties of the fluids. The online algorithm provides the average air fraction in the flow at a frequency of 20 Hz, and the signal can be used both in the study of the flow physics and in control applications. Due to the strong connection between the upstream conditions and the air core behavior that you just saw, the measurements of the wire mesh sensor can be used to predict the core at the pickup tube, for instance in a feed-forward or predictive control strategy. To understand better the connection of the gas core to the upstream conditions, Anand Atmani has been performing CFD simulations in Toulouse. With a fully resolved flow inside the SWIRL element veins, achieved via an immerse boundary method, her simulations start tracking the upstream bubbles individually and shift to a volume of fluid approach when they accumulate in the center of the pipeline, coalescing into a core. At this point, it's clear the connection between the gas core and the upstream flow. Now, it's time to explore the link between the gas core and the valves at the outlets of our separator. This video shows a stable core obtained for upstream bubbly flow. As you can see, the core remains the same over the entire recording. When a sine input is made at the pickup tube valve, we observe that the air core oscillates at the same frequency as the input. This indicates that the valves can be used to adjust and control the core size and therefore our separation. Now that the connection between the core and the valves is clear, we can proceed with building a controller for this system. But first, I must introduce you to the system we use to measure the gas core size near the pickup tube in real time, an electrical resistance tomography. The equipment is no longer present in the loop, but it used to be placed in the spunk pipe very close to the pickup tube. So the pickup tube was up here. Here's a picture of the ERT system installed in the loop. The ERT hardware was developed by Roxol, and an application-focused online processing algorithm was designed by Muhammad Sattar in his PhD. His algorithm reads the currents measured by the device in each one of these electrodes and uses them to calculate the core size and position at a frequency of 10 Hz. Two classical feedback controllers are used to control the separation based on tomography. These controllers link the measurements of the gas core near the pickup tube, obtained by electrical resistance tomography, to actions in the pickup tube valve. The controllers are validated against disturbances in the airflow rate in the loop. The first feedback controller explored in the analysis was a bang-bang controller. The bang-bang controller corresponds to a simple switch between two pickup tube valve positions, based on a certain threshold in the core size. If the valve is kept 50% closed, which is ideal for a low flow rate of air, we observe that the gas core grows in size if a step in the airflow rate is made. When this happens, the core gets too wide, and air is lost to the water outlet, resulting in a poor air efficiency. Now, if a bang-bang controller is used to open the valve to 30% closed when the gas core gets too big, as an attempt to capture the extra air in the flow, we see that the controller is able to keep the core more or less the same size after the change in the airflow rate. If we compare the new efficiency of separation with the controller on, with the previous one without the controller, we see that we got a gain of 26% in the air efficiency with a loss of 12% in the water efficiency. Overall, if we take a common average between the two quantities, we could say we achieved a gain of 7% in the efficiency of separation, just by turning the simple controller on. To generalize the approach for any disturbance in the flow rate of air, a PI controller was designed. The PI controller is validated against a square wave in the airflow rate. As we can see, without the controller on, the core size oscillates following the changes in the airflow rate in the loop. Now, if the controller is turned on, we see that the core size is kept around the set point of 0.2, independent of the disturbances in the airflow rate, indicating that the controller can successfully suppress the oscillations in the core size. However, this particular case has no gain in efficiency in relation to the uncontrolled condition, due to the disturbance being roughly symmetric in relation to the point of operation. As consequence, in the uncontrolled case, the changes in efficiency caused by changes in the core size cancel out, and the efficiency of separation is more or less the same, controlling the core or not. Our results show that tomography can be successfully applied in the control of multiphase flows, represented by the good performance of the control in terms of core size in both the bang-bang and PI applications. However, to choose an adequate point of operation and design a control that improves the efficiency of the process, a careful analysis of the complex link between the distribution of phases, the disturbances, and the efficiency itself must be made. Thank you for your attention. For additional information about us and the results of combining tomography and control, please check the TOMOCON website, tomocon.eu. There you can find more information about our industrial partners, additional applications of tomography in control, and links to our publications.